Hi, everyone. Okay. So my name is Cecile Rousseau. I'm with the Ocean Ecology Lab. I started at NASA in 2011. And I've been working on Earth system modeling. And then I moved to the Ocean Ecology Lab to work with PACE and the assimilation of ocean color data into models. I have managed to make a whole presentation about Earth system modeling with not one single equation. So rest assured, I'm not going to go down some boring talk for half an hour. And it's fairly short, so there'll be plenty of time for questions. But if you're not getting what I'm saying, stop, raise your hand, ask questions. Okay, so I'll be talking about why models. This is a modeler lost in a clean room. AKA me. So the beauty of being a modeler at NASA is that you get to be very in close contact to developing mission, which makes you understand all the intricacy and the challenges of putting a mission into space. I'm going to be talking about the type of models, what it takes to make a model, and then I'm going to show some examples of how to use model and ocean color together in various ways. And maybe inspired to be a modeler one day. So let's start with a definition, a very general definition. So we are talking about Earth system models here, not statistical model, not artificial intelligence, anything. This is Earth system model. And a model is a representation in the form of equation, code describing process. And this is the important part to the extent of our understanding of how ocean works. We cannot model something we don't understand. So the models are only as good as the process that we know of and we understand. So that's always something to keep in mind when you hear model data or you look at model, is that there is some assumptions that are being made based on our knowledge. Now, oceans can be of a variety of complexity. Earth system model tends to be fairly complex because there's a lot of processes and parts to it, as you will see. But if you look at the ocean, just looking at this is just the physics, you see already that, well, I don't know if you see because the screen is small, but there is a whole bunch of processes that have to be included in the model. On top of the processes, you have what we call boundary condition. Boundary condition, if you think of the ocean as a box, you need boundary condition at the bottom. You need to say what happens when something hits the bottom, what happens on the side. So if you have a river, are you going to take into account rivers or not? And then you need to say what happens at the top. Does it exchange with the atmosphere? Does it not? Are you just giving real data to the model? There is also a strong coupling between all those processes. So you can have a physical model, like a circulation model, and you can then add an ocean biogeochemical model. So now you have interaction between your physics and your ocean biogeochemistry. Not all Earth system models have every single component. It's every time a decision between the complexity of the model that you can have and what you can run. The supercomputers that we have are still, limited in some ways, and you can't run everything at a very high resolution with all the processes included on an hourly basis. We just don't have the technology for that. So we cannot resolve everything, so it's always going to come down to the best model to use depends on what your question is. And so yeah, what you're trying to achieve there. Now, another way of thinking about the complexity of models is looking at the range, the spatial and temporal range of processes and how they occur. And so you can have a very simple model here that just represents one process, vertical mixing, for example. And that will be very quick to process, so you can probably run it on your own computer too. And then you have the general circulation model, GCMs, or Earth system model. And they have a lot of processes. Now you're going to need a supercomputer to run it. And they take a longer time to run. Depending on where you are on that line, you are going to resolve different processes. So Earth system model, you can get to climate change if you run for long enough, climate variability, so El Nino, La Nina, eddies and all of that. And on the other end, you have things that are very molecular processes, vertical mixing on one dimension, etc. Another aspect of models, and this is really just so that you are aware if you ever have a conversation with a modeler of what they are talking about, is that there is a resolution both spatially and temporally. And spatially you have both horizontal and vertical. And depending on which models you are going to have a different type of resolution, which is going to affect the type of output you can get. So the equations in a model works on every grid cell. So the more grid cell you have, the longer it's going to take to run. You can have a normal grid spatially. And this is very common. The problem is that you see at the North Pole and the South Pole, you end up with a gap with no data. And so the ocean modeler have come up with a very smart trick. And they had put the poles behind land. And they have put 2 poles in the north and 1 in the south, and we call that a tripolar grid. And so one of the poles is hidden behind North America and another one behind Russia. And that way we have solved the gap problem. And then another type of grid is called a finite grid. And this is, instead of being rectangle, now you have triangles, and those triangles can change shape. So you can do it changing shape based on the bathymetry, for example, where your triangle gets smaller and you have a higher resolution when you're in coastal water, where processes are more dynamic and they change faster. And then out in the ocean, you have larger grid cells because things are slower. And that's a way to have, that combination of resolving the processes both in the coastal area and in the open ocean. You might ask yourself, why are we not running everything on this kind of grid? That's because it takes a lot of computing CPUs for us to run. So generally, this kind of grid, you will see it in regional models, not global models. Vertically, same thing. You have, these are just some subset, by the way. You have a series of options. The most common are something we call the Z coordinate. It just means that your layers are fixed. So your first layer, your second layer is always like 0 to 20 meters, then the second is 20 to 40. You can also have terrain following coordinates. This one, the depth changes depending on the bathymetry. And then the last one is called isopycnal, and that's where it varies every time step depending on the density of every layer. Again, this one is more costly than that, but of course it resolves some issues that you get with those ones. So all of that to say that it's all a compromise between how much computing power you have and what your questions are. Any questions so far? No? Okay, now that was the whole physics of it. Now we're going to dive into biogeochemistry because it's Space Hack Week, and that's what's relevant. Biogeochemistry, the definition that we go by is the quantification of chemical species exchanged between the different reservoirs of the Earth and the transformation of those. And there is 3 ways you can look at biogeochemistry. One, you can go out in the field on a boat and sample. Then you get the data of that point in time, and you can be pretty confident of what you're observing. The only issue with that is that it's very hard and costly, and it gives you only a data point at that hour where you sampled for that depth. You can also have a satellite like PACE, and that's great because it gives you a global overview, but the problem with that is that it only gives you the upper layer of the ocean, and it only gives you data for the variables that you have an algorithm associated for it. So if you think of biogeochemistry, for example, we don't have nitrate or nutrients from satellite. Or primary production, we have one, but you don't have the phytoplankton composition primary production. And so every time you have a variable like that of interest that you cannot derive from satellite, that's where models can come in. Also, models allow you to take the vertical dimension of processes and look, instead of just the surface, see what happens with depth. So if you think of export of carbon and everything, this is where model can help. Now, ideally, you combine all these three approaches and you take the strength of each of the approach and you minimize the weaknesses. And this is generally, this can be achieved by taking the in situ data to parameterize your model and then do what we call the data assimilation, where you take the satellite data and you put them into your model. And I'm going to detail a little bit what putting it into the model is. But the idea here is to develop one system that takes all the information that we have in to provide the best understanding that we have of what's going on in the ocean, and look at processes and be like, oh, the chlorophyll is changing here because the mixed layer depth deepens and there is more nutrients or there's less light or whatever. The most basic biogeochemical model looks like that. So we like boxes. Modelers really like their boxes. I don't know why. And so you have a box that's phytoplankton, and your phytoplankton takes nutrients, and then your zooplankton eats the phytoplankton, and then they poop or they die, becomes detritus, which is then remineralized into nutrients. That's the most, and there's a sun to provide light. This is the most basic ocean biogeochemical model there is. It's called an NPZD model. And, people have used it to test various hypotheses, and it's great. But obviously, that's not very close to what's in the ocean, because we have many more than just one phytoplankton, and the nutrients is more than one, and there's mixing and everything. So what we do is, on top of that, we add a circulation model. And the circulation model allows you to look at advection, convection, and when you combine both, now you can say, hey, phytoplankton, you are getting mixed up a lot. So there's more nutrients coming in, so you can grow more. And then you can add a radiative transfer model. And what that model does is that it takes care of the light. So the radiative transfer model might have input data from clouds, and it will look and be like, oh, today there's a lot of clouds, so less light. And it will tell the ocean biogeochemical model, don't grow today. There's just not much light. And all these three components can work together. Now, I will say not every Earth system model has an ocean biogeochemical or a radiative transfer model. The majority will have a circulation model, but the radiative transfer and the biogeochemical model, they are starting to be more common, but it's not ubiquitous everywhere. Boundary condition, I talked a little bit about it earlier. This is, when you run a model, you have to tell it both the boundary, and I think the next one is the initial condition. You have to tell it what you start off with, like how much nutrient is it to start and how much phytoplankton. You can start your model with zeros everywhere, but it's just going to take a very long time to stabilize and reflect what's actually what's happening out there. So we generally start with in situ data, like the World Ocean Atlas for nutrients. And then phytoplankton, we generally choose a fixed concentration and we let it run. Yeah?
And so the ultimate results that you get, it depends on your A priori you are giving, or it just takes a lot of time to adjust? Or your results will change if you change the A priori nutrients or something?
So yeah, that's a good question. So when you start your model, you have, it's like if you were to start a new planet, Earth, and the ocean, where there was no circulation, no wind and everything, you would have to let it run for a while for things to mix up. And one of the things that takes the longest is carbon. And that's because the overturning circulation in the ocean is operating on hundreds of thousands of years in some location. And so the model has to run a long time so that all these processes happen eventually, and you actually get to a world that is similar to what we live in. Just to give you an idea, right now we are spinning up a new version of our model, and we started the spin up in December, and we have just achieved 100 years. So that's 9 months where you're just running a model and you can't really do anything with it. You just look at how it evolves and where it's going, and once it's stable, you go like, okay, now we can start a real run with real forcing data and data assimilation. So it takes a long time.
So is the shortwave or long wave coupled with the radiative transfer model, or they are just separate things?
No, the short wave and long wave, everything will get into the radiative transfer model. Yeah. What else is there? I already talked about that. Oh, and then the last ingredient you need is a simulation file. Sorry. Ocean color, this is probably the thing that is done the least in Earth system model for ocean biogeochemistry. But some models will assimilating satellite ocean color. Physical data from satellite are more common. And then you can also assimilate Argo files, which several regional models do. But the assimilation is like a whole other discipline, and it's an expertise on its own. Some people work on data assimilation all their career, and that's just what they focus on. Okay, radiative transfer treatment of light. Just to give a brief overview of what it does and what it looks like. You basically so your ocean biogeochemical model gives those data, so the diatom, the whole phytoplankton community here, well, not the whole, but those that you have in your model. Then you have your detritus, your PIC, anything that affects light. You get the concentration from your ocean biogeochemical model, and then you have to tell it what it absorbs and how it scatters. And the way we do it is by taking data from the literature. So this is the absorption that we got from the various phytoplankton groups that we have in this specific model. And the radiative transfer model takes those data, combines it with the concentration, and produce those upwelling irradiance. The cool thing about that is that you can modify that to have whatever spectral resolution you want. And we use this model to generate hyperspectral water-leaving radiance prior to the PACE launch to do a simulation data set so that we could see what it might look like, assuming that, of course, our model was right. And then for this model to work, you're going to need to give it a bunch of data, like how much water vapor is, ozone, clouds, aerosols, and then it takes the light that comes down. And then you have the radiative transfer model in the water that absorbs, scatters the light in various ways, and then at the next time step it says, and this is how much light there was left for you to use. And then it does that also in the vertical dimension. So if in the first layer you have a lot of phytoplankton that absorbs, then it will say to the second layer, this is how much light you have left to deal with. Okay, so the model this is the one I work with, so this is the one I'm presenting. There is many of them, but the logic behind it is roughly every time the same. You have an atmospheric model, so that does the wind, the rain, all of that stuff, the clouds and the dust. And that gives you, in our case, the wind pressure, precip, dust that the models in the water need, both the circulation model that you have here. In our case, we use one called the modular ocean model, and then the NOBM, which is the NASA Ocean Biogeochemical Model. The yellow box, that's the radiative transfer model that I was talking about. So you can see it interacts both with the circulation and the ocean biogeochemistry, and it produces, the light that goes back up to the atmosphere. The other configuration you can use is, instead of having an atmospheric model, you can use data. So this is where you take, for example, the clouds and aerosol from MODIS, and you say, this is what MODIS observed. What happens if there's a lot of dust observed in MODIS on your phytoplankton? So this is a case where you would remove that box and take that pathway instead and provide the data to the circulation and the ocean biogeochemistry instead. We call that coupled. We call that data atmosphere. So if you hear those terms, this is what it means.
Can I ask a
Yeah.
Yeah, so I'm familiar with this one. Like, what is the difference between the MIT GCM and like the geo circulation models?
They're just two different circulation models. There's not a ton. They use Echo, and we use MUM, which is the circulation model from GFDL. The ocean biogeochemistry model, they use something called Darwin, which actually use the same radiative transfer model that we use, so we share that component. And they just parameterize the phytoplankton groups slightly differently than us, but it's roughly the same. The applications are a bit different. We are focused more on developing the ocean biogeochemical model so that it's applicable to satellite mission because it's NASA. So we have done data assimilation for a while. I know they're in the process of starting to do data assimilation, but they're just starting there. The Darwin has been used more for looking at evolution of phytoplankton, and they have started looking at more hindcast, which is when you run something in the present time, so somewhere between 1980 and 2024. That would be a hindcast. So you can do a hindcast, you can do a forecast, and you can do long run. Long runs would be like hundreds of years, and some people do that, but generally you have to reconfigure your model because if you want to run for hundreds of years and want to publish or do research, you have to simplify your model, otherwise you'd just be waiting the majority of your time. But so this is the MIT model, their ocean biogeochemistry model, and it's really cool because it has high spatial resolution in this run, and it shows you how each of the species are distributed and move around. But this one does not assimilate ocean color. Now you might wonder, why do we use ocean color in models? The reason is ocean color has some gaps, which someone might have talked about it, I'm not sure. But there is gaps between clouds, aerosol, and then between the swath, you get gaps too. And so if you end up trying to look in the Southern Ocean, for example, and you just use satellite ocean color data, you will be looking at 6 months, a year of data. And so you are really not looking at a seasonal variability. You are really looking at what happens in summer, spring, but you don't know what the rest of your year is. So if you do that, you are really looking at the interannual variability of spring, summer phytoplankton in the Southern Ocean. If you take the satellite ocean color data and you assimilate them, now you can provide a global coverage. You can also start looking at the vertical dimension. And by doing that data assimilation, you end up reducing both the bias and uncertainty of both the model and satellite data. So it's making the use of both data set and using their strength to produce a product that is, at the end, more robust, especially in areas that you don't have data, that you have gaps. The other point, I made it earlier, models can be used to prepare for satellite mission. They can also be used to prepare for field campaign. There's something called observe simulation experiment, where it's OSSIs. And you basically use the model to say, hey, if I went with a boat and I sampled these 5 data points, or these 10 data points but only 1 depth, which one would bring me more knowledge? And depending on the answer of that, you can start designing your field sampling to be more robust or give you more information at the end. So OSSIs are something that we use a lot to do that kind of work. It can be used for future satellite mission as well. So if you're trying to see whether mission A or mission B would be more valuable, you can do an OSSI and see which one would bring you the most information, reduce your uncertainties, and be the more bang for your bucks, basically. And then you can do future climate scenario, which I'm not going to talk much about it because it's not what I do. But of course, if you were to think what would happen in 100 years with increased CO2, you can use that and test various hypotheses. I put this plot here because I thought it highlighted very well that when you look at the global carbon cycle, you have a lot of different pathways, and each of these pathways cannot be deduced from satellite data. And so by, if you want to know, think about the vertical sinking of carbon or how much nutrients you get from upwelling, this is where the model are a good tool to do that. Data assimilation. I have simplified the most I could. Data assimilation. So this is just so that you have heard the term, you know what it does, and I'm not going to go into details about it because it's a whole thing. But this is what it does. So that's a daily image that you get from satellite ocean color. So you see a lot of gaps in the Southern Ocean and in between each swath, and then some where you have dust. You assimilate those data into the model, and this is the output you get. And so you have now a complete coverage. The white is where there's ice, by the way. So that's what you get. Now you have two big categories of data assimilation. You have variational and sequential. I'm not going to go into details, but they just do things a bit differently. Again, the one you choose depends on what kind of resource you have and what data you're working with. But if you look at, you have the observations, which could be your PACE data, for example, and then you have your model here, so unconstrained, so on its own. And what the assimilation does is that it brings the model closer to the observation. It doesn't make it match completely, and there's a lot of, science behind of how much you get it closer to. For example, in some cases, we have found that the satellite data had a higher uncertainty, where there was dust, for example. And what we do is we give more weight to the model rather than the satellite during the assimilation in those locations, and you can change a little bit that. So it's not that you do that everywhere the same amount. When we do assimilation, it affects chlorophyll, not the phytoplankton types themselves. It affects chlorophyll, and then we call it multivariate because depending on how much it changes the chlorophyll, it also affects the nutrients, but it doesn't affect the composition. Another way of looking at this is this is the model running, and you have the first time step. Your model tells you that, and then it sees that the satellite sees that. This is what you would end up with. So it's an adjustment. It's not a complete match to it. And what we hope to do next in the NOBM is to start assimilating the phytoplankton types from PACE. So that's, if you were wondering where we are going.
So, okay, so you're assimilating the chlorophyll, and then you're like backtracking the phytoplankton types. Like, how do you get the phytoplankton types to also assimilate?
Well, right now we don't assimilate phytoplankton types. Right now we just assimilate chlorophyll. And then depending on the condition that there is, so if there's more nutrients or whatnot, more silicate, you will have more diatoms. And that assimilation, just affects the total chlorophyll that gets split up into the various phytoplankton groups.
Okay. Based on, like, you're using information about the condition.
Yeah, yeah. I was going to say something else, but I forgot. Anyway, so that's that. A bit more detail. You heard me say earlier that it was reducing the bias of uncertainty. This is, if you wanted in numbers, what it would look like. So that's when you assimilate chlorophyll. That's what the model without assimilation looks like. So pretty good distribution, but you see, for example, in the North Atlantic and North Pacific, the model overestimates the chlorophyll compared to the satellite data, which means that once you have assimilated, you can see that the chlorophyll is less there. That can be because your model is missing some processes, but in some case, it can also be because your satellite data does not have data somewhere. And so if you have a cloudy day, and you don't have data, and then the next day you have a sunny day and your phytoplankton grows, if you average those two, you're going to overestimate how much chlorophyll you had because you just looked at the days where there was a lot of sunshine and the phytoplankton was growing. And then, so yeah, your bias goes from down to 0.1% once you have assimilated, and it reduces the uncertainty and bias of the model as well. Yes. Great. Hi.
Is there any top-down components in the models?
You mean like zooplankton grazing? Yeah, there is zooplankton grazing. I mean, I'm not gonna lie, we have only one zooplankton, so it's very basic. Kim laughing. It's like just one zooplankton, silly people. Again, it depends of what you're. Obviously, I would not use the NOBM to look at the effect of vertical migration of grazers on something. That's just not what's represented. That being said, you can always add processes, and so once you have the data, you can add that in the model. And that's where we're mostly, we didn't just wake up one day and decided, oh, well, we're just going to put one grazers because we don't care about grazers. It's mostly related to how much do we know about grazers, how much data are out there. And there's just not. It's really hard because every time you look at the data, there's a lot of variability. And how can you represent that in a fairly simplistic manner? It's, again, a balance. You have to choose. And if you told me, oh, there's 5 zooplankton groups, each of them graze that much, they die that fast, and they are that big, then I can add that to the model. That's not a problem. But it's just a lot of uncertainties on the data leads to us not being able to model. Now, that being said, there is some models that do zooplankton grazing in more details than we do. There's no doubt about that.
So following up on that, then, so why do you include zooplankton? Since you have the phytoplankton, you could get that arrow going into detritus by sort of kind of incorporating.
Well, because phytoplankton can either die on their own, or they can get grazed. If you get grazed, then there's a temporal component to it, right? They don't just die and sink and get remineralized at the same speed as if they go through the zooplankton process. That will take longer.
Have people compared models with and without zooplankton to try to see which one is better?
I don't know. I'm not to my knowledge, but that would be an example of a good use of a model where you could run the NOBM with the way we have it and then do what you say and see the difference and then be like, okay, this is how much grazing affects what we are seeing. So that's a perfect example, thank you. a small exercise, and you can play pretend a lot with models, which is, one very fun thing. Yeah.
On the other hand, how can we tell which one is better?
Again, we need data. It always comes down to that first definition where unless we understand a process and we know what it's like, it's very hard to bring it to the global scale. So we need data for the model development, validation, to get it to the next step of giving global data.
So your data simulation model, component, is that a interactive component?
Yeah.
Does that feed back to the control run, for example?
Yeah. Every time step, it updates, yeah.
So if this is the case, which satellite source do you use for the data simulation to feed back to the free run?
We do CWIFs, MODIS, VIAs, and we use the data chlorophyll, particulate inorganic carbon, and the absorption by color dissolved organic matter. So we assimilate all 3 of those products.
So it's a merged version of the...
Yeah, well, that's a whole other topic, but yes. The short answer is yes. If you want me to talk, I can talk about that. But yeah, the merging thing is a whole other topic. A word of caution, and that's more, again, if you were to use model data or try to, do something with models and ocean color, quantities measured in the field, satellite and models are not the same thing. That's something to keep in mind. The satellite, even PACE, does not observe chlorophyll. It's an algorithm. Your model does not, simulate chlorophyll directly. It's deriving chlorophyll. there is a mismatch spatial and temporally between in-situ satellite and models. If you are to try to validate, your model with satellite data, for example, just know that the satellite data observe that specific area at a time of the day. Your model does one time step per day generally. Also, there's a mismatch vertically because your satellite don't observe everything vertically. Your model has several layers, so it will. And then some area of the world, like I said, do not have data for extended period of time. So if you're comparing a month of PACE data with a month of model, that is not probably a very fair comparison unless you have 31 days of both data sets. So something to keep in mind, especially when you're working in region where there's a high heterogeneity, think coastal waters, high seasonality in dust clouds, all of that. Now, let's move on to some cases of what we have done by using models and ocean color. One of the most recent work that we did, Lionel, who was supposed to be here today but is on vacation, did just publish a paper where he used the ocean biogeochemical modeling assimilating ocean color data to look at what we call the blob, which is a marine heat wave in the North Pacific. And you can see both in July 2015 and August 2019, you had very high temperature here. And with that, there was actually a lot of effect of that blob on higher trophic level. There was, a decline in whales and salmon and squid, which the communities in that area really rely on. And on the other hand, you had some winners, so there was clearly a shift in the higher trophic level. And what Lionel did was, he was like, well, can we trace this back to something going on at the lower trophic level? And it turns out there was a paper by Whitney in 2015 that already looked at the chlorophyll, and they found that there was a decline in the phytoplankton biomass, so total chlorophyll in that area during the first blob. And so our question was like, during the blob, is all phytoplankton groups declining, or is it a phytoplankton composition shift? So he took the NOBM and he looked, and you can see that there was, in some areas, a phytoplankton composition shift where diatoms, and the green one is others, but it was traced back to the dinoflagellate increasing in the Gulf of Alaska region. And then in another region, the marine heat wave had a different effect. And now you had a switch between the diatoms was declining, which is why looking at total chlorophyll, we saw a decline. It was mostly due to diatoms. But on the other hand, you had a coccolithophore that went up. And so it's a dynamic system where if one declines, the other one found an opportunity to go up. This is not always the case. In that paper, if you go look, you will see that in the Equatorial Pacific, at that time of the year, something different happened and everyone declined. So it was not a shift, it was just a decrease in phytoplankton biomass. So again, using the model, this is what you can do. The other thing that you can use models to is to look at future satellite mission or field campaign. I've talked about it. This is an example where we use the radiative transfer model and NOBM to generate the hyperspectral water-leaving radiance in preparation for PACE and start looking at what we might see with PACE. Now the question is, was it right or not? This is where we're going to go, in the next few months for us. And this is it's supposed to be an animation, but I don't think it's going to work. There you go. This is the atmospheric model from NASA, and it shows you what you can do with it. And in orange, you see the dust. The green is sulfate, and then red is carbon, and then the greenish, bluish is sea salt. And so this is the type of thing, this is called a nature run because it's a very, very high spatial resolution run that we developed to make OSSIs, so those, play pretend run. And this, allows you to really look at the global scale, what, things are happening, where things are, and if you combine that with the ocean, then now you can look at the various atmospheric ocean, coupling. Okay, takeaway message. Ocean models are a step-by-step function that is only as good as what we understand. You can combine ocean color and models in various ways to try to get the most information out of both approach. There is a few words of cautions on things not to do. So if you ever work with model, make sure that an ocean color. Or ocean color, make sure you talk to the people that knows about it and that you don't compare apples and potatoes. And, models are becoming more and more open sources. The NOBM, for example, is on GitHub, it's available to everyone. More models are becoming like that. So, we are really trying to make it more available and usable by the community. So. That's it.
So if it's available on GitHub, I imagine it's probably really big data files you still need to run it. How does that work?
The data files are not that big. It's how you're going to run that is still the problem. The data files were just the satellite data that you just downloaded, the same thing. The idea is once that open, data science is getting better and better down the line, we would like to have everything on the cloud so that you can run the model without downloading the data and just link it back to the satellite data and run that way. But right now, that's not something that is available or possible, but that's where we are aiming for. So we have the code now on GitHub. Now, if you don't have access to a supercomputer, you can run little, bits of the code as a one-dimensional model that you can do, but you wouldn't be able to run the whole global Earth system model with data assimilation.
Do you also estimate gap in ocean observation data? There are a few methods which do the gap filling in daily data, or for example, SSW, not OCCCI.
Yeah, no, we don't.
Okay.
We don't because it's two different approach to get to a gap filled. The OCCI does it a certain way. We just assimilate. So it's a different way of getting to the same end results. But yeah, the Earth system model just is one of the product it provides is that, but that's not the sole intention of it. Okay. Oh.
Sorry. The resolution of the data that is produced by these models?
Good question. Right now, the new version we are working on, that we're spinning up, that I mentioned, is 1/4 of a degree. The old version that we have used so far is 2/3 of a degree by 1.3. So it's much closer.
Is the resolution, if you want to get the output at a very high resolution, the computational rate exponentially improves?
Yeah, I mean, it increased quite a bit, yeah. Yeah, it's much harder to run. The new model that we have is much bigger because it also has an atmospheric model. The previous version was just data atmosphere. The new one can be run data atmosphere or coupled. That's a switch you can turn on and off. And the resolution, both spatial, like horizontally and vertically, is much higher on the new version. Ian.
I know, like you said, people spend their careers on assimilation. Can you just like summarize like what's the framework for assimilating chlorophyll that you guys use in the NOVM? Because like I know sometimes like your framework can like really impact like how you actually do the modeling and like really slow things.
Yeah.
Take a lot of time or someone like me.
So the old version, we used something called CRAM for conditional relaxation analysis method. It's very much like on the plot where you just, change somewhat the data depending on where you are. For the new version, we use something called JEDI, which it's a project that is between NOAA, NASA, the Air Force, and the idea is that you develop that kind of data assimilation code, and then you put it on GitHub, but the code is developed in such a way that anyone can join their model to that data assimilation. So the code that we are developing, for example, NOAA was working with us so that it would work with their own code of the model. So you could have the ocean biogeochemistry model from NOAA, the one from NASA, maybe the one from MIT one day, that just use the same data assimilation approach, just have different models in the background. But that's, again, we're stepping up in terms of how much it does and how it does things. So it's a lot more complicated than the good old CRAM.
Jedi with a J or a G?
Jedi with a J.
Okay.
Yeah, there's a lot of Jedi. It's really confusing.
Can you say a little bit more about the impact of PACE to the model?
How we use PACE of the model. So we are trying to work with the JEDI team to get the PACE data assimilated. Right now we are a little bit in a hiatus because the NOAA person moved to somewhere else and the funding dropped. So we are, kind of waiting a little bit here. But yeah, the idea is that we're going to start looking at those simulated data sets and see how well we did. And then we're going to look, to assimilate the PACE data at some point. But yeah.
Do you assimilate readings data or you assimilate the IOPs?
So in the past, we have assimilated chlorophyll PSC acidum. For PACE, we plan to start assimilating the remote sensing reflectance themselves. And we want to do a test run where we assimilate chlorophyll and then remote sensing reflectance and compare those two and to see how well they disagree. Okay. Thank you, everyone.